Good afternoon, everyone. My name is Gonzalo Behrman. Those that don't know me, I'm an infectious diseases specialist, chief of infectious disease here at VCU Medical Center. It's my great pleasure and honor to introduce our speaker today, one of ours, Infectious Disease Service, Dr. Daniel Nixon. Dan's been with us since 1997. He's currently an associate professor. He's also the director of the HIV or the Infectious Disease Clinic here at VCU Health. Dan did his training in Ohio and came to VCU in let me see if I get this right, 1993 to do this clinical infectious diseases fellowship with us and has stayed with us ever since. It should be noted that Dr. Nixon also did a postdoctoral fellowship in molecular virology. He has a PhD. His area of interest is include translational research involving trials of HIV and associated inflammatory conditions related to viral infections. I would be remiss not to mention that Dr. Nixon has also received the Department of Medicine Distinguished Research Awards back in 2006 and 2009. So having said that, it's my great pleasure to introduce Dr. Nixon to the rest of the group for today's grand rounds on a molecular approach to treating MDR or multi-drug resistant gram-negative rods. Thank you. Take it away, sir.
Thank you, Gonzalo. Hopefully everyone can hear me, but I'm pleased to be able to talk today about a molecular approach to treating multi-drug resistant gram-negative rods. One of the more interesting, challenging infections, which include Suzy Monas, aka Pseudomonas, and her non-alcoholic friends, aka the non-lactose fermenters, Acinetobacter, Stenotrophomonas. We'll meet those guys. Let me just say that, as Gonzalo said, I particularly enjoy molecular biology and immunology. And although I've used bacterial cultures for many, many years and sensitivities where we drop a disc or an e-test on a plate, I always found that slightly less than as satisfying as tearing into a good genotype with a complete molecular breakdown of the resistance mechanisms of, say, HIV and coming up with a targeted strategy. So in recent years, as the technology has evolved to do that, I became very interested in this. And so we'll talk about one of the more challenging places where this is applied. You'll maybe note that after my associate professor, I added U.S. Naval Air Controller, retired since well before medical school. And I do tend to think of our ongoing battle against global infectious diseases in military terms. There are a lot of parallels. So we'll kind of highlight a few of those just for fun. Let's see here. So there we go. No relevant interest to disclose. The objectives of this talk are to better appreciate the rapidly evolving and global threat posed by infectious organisms. Not even sure you need to have that one in our current situation. To appreciate how with multi-drug resistant organisms such as the gram-negative rods, there's actual clinical value in determining the molecular mechanisms of resistance, not just an antibiogram. And to examine how newly approved gram-negative rods antimicrobials can overcome some of these more challenging resistance mechanisms. So going back to 1960, the height of the Cold War, the U.S. arsenal was broad and powerful, but relatively unsophisticated, as exemplified by the B-52 bomber at the bottom. This thing could drop literally tons of bombs that would be very devastating, but they were rather imprecise. And the unfortunate collateral damage here was civilians, infrastructure, et cetera, et cetera. Its contemporary polymyxin B, now basically Colistin, was similar. It packed a punch, but it had collateral damage in terms of basically putting nephrologists in work. Interestingly, both these weapon systems are still in use today, however modified to make them a little bit more precise. Move to 2020, and things have gotten more sophisticated. At the bottom panel is the F-35C, which is the carrier variant aka Navy variant, of the F-35 fighter attack aircraft, which is probably at the leading edge of sensor technology and possibly stealth. This aircraft has numerous sensors with incredibly high resolution, allowing one aircraft to invade unfriendly airspace that is heavily guarded, heavily defended, lock up multiple air and ground targets, and then assign these targets to either itself or an accompanying squadron of heavily loaded non-stealth aircraft or cruise missiles off a base or a destroyer. Basically light up the targets, track the targets, and get out of harm's way using its stealth capability. Above that is the drug cefiderocol, which we're going to talk about. It also uses stealth technology and advanced targeting. These are both game changers in theory. Neither has actually ever been tested in combat. The Israelis have flown a few F-35s. The cefiderocol has fought some UTIs, but limited duty on the front lines against, say, a ventilator-associated pneumonia. The enemy that we'll discuss today is the emerging threat of multi-drug resistant gram-negative rods. Carbapenamase resistant Enterobacter, the CRE, multi-drug resistant Acinetobacter, which we'll talk a little bit about, and most of the talk will be focused around Pseudomonas that is multi-drug resistant, basically carbapenem and possibly other things resistance. These guys result in thousands of deaths per year in the United States, many dollars in morbidity, and globally, tens if not hundreds of thousands of deaths. It's important to note that the magnitude of this threat is much greater in other countries. We in the United States and at VCU are relatively more fortunate not to have so many multi-drug resistant gram-negative rods, such as in the case of Pseudomonas, we actually have 90% sensitivity to meropenem. And if you look here, pretty much near universal with a few exceptions, sensitivity to everything else but Acinetobacter that are on this panel, which is excellent. And this is a testimony to the microbial, antimicrobial stewardship program, the hospital epidemiology program, to keep that number of sensitives high, to keep the number of resistance low, because then we don't have to do too many of these exercises that I'm going to talk about, because they're cumbersome, complicated, and use very expensive drugs. First case of Suzy Monas is a 64-year-old gentleman from Vietnam originally. He's got several medical problems, including pretty bad emphysema. He came to us on January 21st with fever and hypoxemia. But before that, he had actually been here for 2 months until January 8th of this year with hemoptysis, found to have a large cystic mass in the right hemithorax, had a lobectomy, full decortication. They found both a mucinous adenocarcinoma and MRSA in tissue culture, which was treated with 4 weeks of bank. Complicated course, kidney injury, dialysis, renal failure or respiratory failure, trach, GI bleed, acalculous cholecystitis, critical illness polyneuropathy, and several bouts of hospital-acquired or vent-acquired pneumonia. After the MRSA, there was serratia, and then finally Pseudomonas. Suzy Monas rears her ugly head on December 12th or December 2nd, and at that point was fully antibiotic sensitive to the usual anti-pseudomonal, cefepime, zocin, et cetera. After that, despite appropriate treatment, it continued to show up in every respiratory isolate. And by December 21st, or under 3 weeks later, was now fully resistant to meropenem, zocin, intermediate to cefepime, still showing quinolone and colistin activity, along with activity to some of our newer agents, which we'll talk about, ceftazidime avibactam and ceftolozane tazobacterium. I think I'm alternating between zone and zane. I apologize. He ended up completing 2 weeks of ceftaz avibactam on 1/8 and was sent out to Vibra, had finished antibiotics at that point. But the problems continued at Vibro with persistent fevers, persistent leukocytosis, increasing purulent drainage from a right chest tube site that was just a hole at this point. They were treated at Vibro with Vanc, Flagyl, Aztreonam. After seeing some more of the sensitivities, they added Colistin on the 16th. On the 18th, again, grew the multi-drug resistant Pseudomonas, hypoxemia, more vent support, back to VCU with ongoing fever, and a chest CT that basically showed ongoing effusion, progressive airspace disease, very densely socked in this right lower lobe, with swelling around the site of the chest tube, indicating probably some soft tissue involvement as well. Now, these are the sensitivities when it initially became resistant to meropenem from December 21st, showing what we talked about, and sensitivity to ceftolozane, Tazo, and ceftazidime avibactam. However, remember the patient was put on ceftaz avibactam, but if you look at the date on this, January 3, I don't think that the treating team was even aware that this addendum report had come out, because as per our excellent molecular services at microbiology, they subjected to this patient to some molecular testing, which we'll talk about, showing that no carbapenamase was detected. Anybody have any thoughts on that in the front row? So, not really set up for questions, but the avibactam, its job is to defeat carbapenamases, particularly KPC, OXA48, some others. It was not the avibactam that was adding much to the activity of this drug over ceftazidime, except perhaps more activity against AMP-C, which we'll talk about. But there's a warning sign in that our weapon of choice here probably wasn't hitting the molecular reasons that this patient had become resistant. And sure enough, it did show up as resistant on the subsequent panel. This is a broader panel, which is useful sometimes, the CF panel, cystic fibrosis, where we added a couple things. It does the amikacin, it does imipenem and meropenem. So kind of a little bit more useful. Still sensitive to ceftolozane azibactam. Okay, another satirical question. Why do we need to spend $100 million per copy of an F-35C aircraft? Does it drop more bombs? Does it fly faster? No, it actually doesn't do either. It actually flies slower and has less bombs. It is capable of evading warplane resistance mechanisms. As in this one, probably the most formidable warplane resistance mechanism on the planet, made by the Russians, the S-400 surface-to-air system, which has advanced targeting ability, even possibly a match for our stealth aircraft. We don't actually know, it's hypothetical. Bacterial resistance mechanisms in the gram-negative, certainly, are no less formidable. Here's the basic systems that they employ. Efflux pumps, basically pumping the drug out of the cell. Porin mutations, basically blocking its entry from the cell, along with enzymes like B-lactamase and other KPC, et cetera, metallose, and target site mutations, which would be relevant to things like quinolones and aminoglycosides and things like that. To enter the cell, beta-lactams and quinolones require the porin, and they will be vulnerable to these porin site mutations. Not so much for aminoglycoside and colistin, which use other sort of mechanisms to enter the cell. Pseudomonas is very intrinsically resistant. As you can see, we have some opportunities in the beta-lactam family with the piptazo. We have ceftaz, cefepime, aztreonam, meropenem, and we have some options with the colistins, the aminoglycosides, not listed, the quinolones, But we're out of luck on the tetracyclines, the bactrums, the chloros, the phosphos. So it's a rather narrow set of weapons that we have to choose from. And some of them, including the aminos and the polymyxins, colistins, are pretty toxic. So the beta-lactams, we'd like to make that work, if possible. Focusing in a little bit more on Pseudomonas, the intrinsic systems that it uses include outer membrane permeability regulation, aka OPRD being the primary porin that it downregulates, efflux pumps, the MEX system, MEX, basically increased expression, pump antibiotics out of the cell, antibiotic inactivating enzymes that we mentioned, target site modification, less relevant for the beta-lactams. Briefly, I'll mention that a lot of this stuff is intrinsic, can be upregulated depending on the circumstances, but there can be horizontal transfer of resistance genes, there can be mutation, and we won't really go into the adaptive resistance of Pseudomonas and other organisms that include basically biofilm. And if you want to talk about biofilm, we have the cystic fibrosis sort of upregulated strains where they're mucoid and create quite a bunch of havoc with this mechanism. Particularly, Pseudomonas defenses against antibiotics start with the upregulation of AMP-C beta-lactamase. This is one of the most prominent defense mechanisms. So this is normally present and confers resistance to the lower level penicillin, ceftriaxone, and other antibiotics. It doesn't take a lot to de-repress or upregulate AMP-C, which allows it to defeat agents like piptazo. Now, to acquire resistance to carbapenems, which is where we'll kind of focus, and cefepime, you generally have to do more than just de-repress AMP-C. And the main strategies it will employ are what we've mentioned, the efflux pumps, the downregulation of porin, and other beta-lactamases such as KPC. Pseudomonas is interesting, worthy of this, focus, because the other Enterobacteriaceae, the lesser challenging organisms, are somewhat more predictable. For example, you can pretty much tell by various patterns, like look at this Citrobacter serratia, for example, resistant to cefepime, probably an ESBL. Sensitive to cefepime, but resistant to triaxone, almost certainly a de-repressed AMP-C, because cefepime is stable against AMP-C to a fair degree. But cefepime resistance, we know AMP-C is going to be there and stuff like that. That's not really going to answer the question. Zosin variable, it's essentially not predictable. We need help. So this is kind of an approach to dealing with this problem. Step one, evaluate the beta-lactamase. Here we're going through the Ambler classes of beta-lactamase, which I certainly wouldn't expect most of you to know or care about. But by way of background, class A, that includes your standard ESBLs, but also like KPC, Clebnemune carbapenamase, which kind of was one of the first of these bad boys to sort of show up in the United States. These are the metallos, less in the United States, more in developing countries, still occasionally in the United States, IPM, NDM, VIM. Class C is the cephalosporinase, AMP-C being a sort of a prototype. And then class D is another class of beta-lactamase, the OXA48-like. Interesting here that we'll talk about, some of our beta-lactamase inhibitors get KPC and OXA, and some only get KPC, and that's important to know. This is courtesy of Dr. Chris Dorn, who runs our clinical microlab, which is the wind under the wings of the infectious disease. This is our cue if we are James Bond. This is the guy that makes all the important technology to allow us to fight the crowds. In this case, this is his recipe for Carbapenamase testing. It is done automatically on meropenem resistance for all Enterobacteriaceae and the non-CF Pseudomonas, other organisms by request. And it looks for your KPC, your metallo-beta-lactamases, and OXA48. Note that these metallo-beta-lactamases are not inhibited by avibactam, vaborbactam, and relbactam, which we'll talk about. But aztreonam is active against the metallos. Unfortunately, many times the Crobe also includes other mechanisms to defeat aztreonam. So, in our case, we can't directly measure what we need to know. What we've learned so far is that it's going to be making AMP-C, check. It might be making a carbapenamase, wasn't. And then it's likely to go for strategies 3 and 4, downregulate porin, upregulate efflux pumps. Can't measure that directly. Clue number 1, our case is resistant to both meropenem and imipenem. Meropenem is preferentially pumped out, or I'm sorry, defeated by porin mutations. Imipenem is somewhat more defeated by efflux. This gives you a little hint. It's not definitive, but maybe both are involved. Maybe not. There was no KPC or OXA48-like. Remember, we talked about as avibactam is active against 48. These two are not. KPC, all 3 of them will hit this. There was no metallo-carbapenamase. Hyperproduction of AMP-C expected, but that wouldn't cause the carbapenem resistance. So with 99% probability, I think we could say in our case study, yes, that efflux and porin in play, and knowing that these are co-regulated frequently, tell me that they're probably both in play. So we're going to need strategies to deal with that. Just briefly, a lot of new drugs have been approved or been given new indications over the last couple of years. Some of them are fairly hot off the press. Ceftaz avibactam, approved in 2014 for UTI. I think it's approved now for healthcare. Zerbaxa, ceftolozane, Tazo, got the initial approval for the UTI stuff, and as of last year, healthcare-associated pneumonia. Cefiderocol, just approved in November for UTI with other indications being studied. Imipenem, relbactam, it's got the indications approved last year for UTI and complicated intra-abdominal. And I didn't have on this slide meropenem, vaborbactam, in many respects similar to imirelbactam. So in our case, remember after the KPC, let's see, was not identified, but we lost the activity of ceftaz avibactam. It pointed to upregulation of efflux and downregulation of porin. This is ceftolozane Tazo against carbapenem-resistant non-carbapenamase producing, AKA just like what we were dealing with in that case. I think they looked at about 40 isolates, 41 isolates altogether. And these are isolates that they characterized the resistance mechanism. Decreased porin activity, OPDR, 95% sensitive ceftolozane. Overexpressed MEX-B, MEX-D, or MEX-F. This is the efflux pumps. Very little resistance to ceftolozane Tazo. Hyperexpression of AMP-C, again, mostly active, maybe 5% resistance. All comparing very favorably to ceftaz avibactam. Ceftaz got avibactam, and its main trick is to defeat carbapenamases. It doesn't do, it'll help with the AMP-C part. It will not do anything against these efflux and porin mutations. It will be defeated. Same panel of isolates. the MICs of basically 95% of these isolates were sensitive. This compares favorably to everything on this list except colistin was 100. There is also data in animals, which I will spare you, genetically defined isolates similar to what we were just talking about with MEX and OPD resistance mechanisms. In these genetically defined bacterial isolates with these types of resistance, they were also successfully treated in a neutropenic rabbit model. So pretty challenging model, but the proof is in the pudding talking about people. Now, ceftolozane tazo, you know, there's not a tremendous amount of data on this. This is probably the best study I could find in the challenging case of multi-drug resistant, carbapenem resistant Pseudomonas, where basically, again, cases like our case study, about a 71% success rate. Not bad, but there was a little bit of worry in that 3 patients showed the emergence of resistance. And what was happening here, it was not resistance from changes in more efflux or more pore mutates, it was changes in the AMP-C itself, either increasing its output even more or changes within the AMP-C making it more effective at defeating ceftolozane. So this is very encouraging data, but it's also a cautionary note. Like all antibiotics, we don't want to put too much pressure on this or we'll see that widespread. So then you might say, the heck with the beta-lactams, I'm going to use colistin. That kills everything, right? Well, when you look at Pseudomonas, you don't see a lot of direct data to kind of tell you one way or another if it's better than some of these more newer beta-lactams. But this is data from basically KPC Klebs, ceftazavibactam versus colistin. Colistin pretty much loses. This is ceftazavibactam, 88% survival at 30 days, compared to carbapenem, carbapenem and aminoglycoside, carbapenem, colistin, and others, which include a variety of things. So you sort of come out thinking, well, you know, maybe colistin, you know, maybe not always the best way to go. There'll be a little bit more I'll talk about on that. Right now, our second case of Suzy Monas. This is a 21-year-old previously healthy guy from, well, he was actually in Guatemala. He had a motor vehicle accident. He came to the United States on December 20th, had an AKA with a skin graft. In rehab, he got fevers and leukocytosis. They did a CT scan and it showed a fluid collection, abscess at the distal stump, along with some adjacent osteomyelitis suspected. Goes to the OR for debridement, that's good. Here's what we grew. Resistant to everything except ceftazavibactam, taiga, not really good for taiga, and colistin. Really, ceftazavibactam and colistin. Now, this is sort of the opposite that we saw in our last Pseudomonas. And as one might expect, KPC was detected. So here we chose ceftazavibactam would be the obvious choice. But is that the best choice? It may be just a perfectly fine choice, I think, in this situation. However, we now have multiple choices among these KPC inhibitors, specifically vaborbactam and relbactam. Was it mirovabo and imipenem relbactam? Or I hope I don't have that backwards. Now, this was a study called TANGO. So here we go, avibactam and vaborbactam TANGO with KPC Kleb. Not Pseudomonas. Once again, we don't have much of this data in Pseudomonas. But these were severe Cree infections that got either mirovabo or best available therapy, BAT, which included a lot of ceftaz-avi, also some polymyxins, aka colistin, carbapenems, et cetera, et cetera. basically on this side of the line, cure was all favoring Mirovabo. And these are different demographics, severities, ages, et cetera, et cetera. Here also favors Mirovabo. This was 28-day all-cause mortality. So we get a pretty good hint that what was compared to, which didn't include things like Sofidricol and stuff, Mirovabo did pretty well. So, is that a better choice than Avibactam for a KPC? Well, there are some other advantages in the literature. The MICs with Mirovabo tend to be a lot lower than ceftaz-avibactam. Secondly, the Avibactam can overcome KPC resistance mutations that defeat Avibactam. And when resistance does occur to Avibactam, in KPC at least, it is basically a result of porin mutations, which are pretty rare in CLEP. So you don't see a lot of resistance in CLEP. Now, we do see this, of course, in Pseudomonas. So if you deployed Avibactam here, would you be a force driving more porin mutations, OSPD? Who knows? You get similar sort of story with Relebactam. So basically, at least in CLEB, Avibactam and Relebactam appear more stable and have better MICs, possibly better clinical outcomes compared to Avibactam. Not a wealth of data, but interesting. My final Pseudomonas case. Now this one I got to listen to at an excellent presentation at the Infectious Disease Society conference several years ago, where I ended up wandering the streets after a lot of drinking in New Orleans. But I pulled myself together and heard this excellent case of a gentleman from India with Pseudomonas that was resistant to colistin, aminoglycosides, quinolones, all the beta-lactams, including ceftaz-avibactam, ceftolozane tazo, carbapenamase, estrianum, everything they could find to test. Game over. They tested KPC positive, metallo-beta-lactamase also positive, MDM. What to do? DNR, living will. Hint. They're now trying to develop Acinetobacter Avibactam. What they did in this case, that like our own case, knowing the molecular mechanism helped guide therapy in our initial case, in our subsequent case. And here, knowing this molecular mechanism, they paired ceftaz-avibactam with estrianum, allowing the avibactam to defeat the KPC, while the estrianum was not affected by the metallo and killed the organism. And there have actually been a couple of these now published. Also, you might have noticed that all three of my cases were from people who were not necessarily acquiring the germ in the United States. We had a Vietnam and a Guatemala, and now in India. This fits. There's a lot less multi-drug resistant stuff in the United States, but it's only a plane ride away. Okay, so I want to hit on some of the other non-fermenters or non-alcoholic gram-negative rods, Acinetobacter, Burkholderia, Stenotrophomonas. How do these new drugs stack up, first of all, against these guys? Well, for ceftaz-ava, for Mirovabo, for imipenem-rel, you actually gain no activity against Acinetobacter, Burkholderia, or Stenotrophomonas. That's unfortunate, but their role is not going to really be useful there. Ceftolozane tazo has no gain in activity versus Acinetobacter, at least maybe paired with tazo. One wonders what it would do paired with another beta-lactamase inhibitor. But in any event, it is somewhat more active against than ceftazidime, against these germs, maybe 2 to 4-fold lower MICs. It is difficult to know if there's any clinical utility in that. There may be, and it may be something that comes up into consideration because these are guys that we don't have a lot of options. But the next drug I'm going to talk about is very active against almost all isolates, multi-drug resistant Pseudomonas, Burkholderia, Stenotrophomonas, Acinetobacter. That would be cefiderocol. Cefiderocol, approved in November. It's a novel hybrid. It contains a cephalosporin and a siderophore. The cephalosporin is a lot like ceftaz or cefepime molecularly, but it contains this cat-coal siderophore moiety that basically uses necessary bacterial iron transport systems to enter the cell, bypassing the whole porin situation. So none of that porin mutation stuff is going to work to defeat cefiderocol. Certainly, it's possible that changes in iron transport could. This antibiotic is fairly amazing. It would be the only beta-lactam that defeats class A, KPC, ESBL, class B, metallo, class C, AMP-C, class D, OXA48-like defense mechanisms. Pretty freaking awesome. Active against just about every gram-negative rod out there. Check this out. This is thousands of isolates. Enterobacter, Acinetobacter in red, Pseudomonas in green, Steno in purple. And look at this. Almost all the isolates have an MIC less than or equal to 2 microgram per mil. Down here, you can see that's 100% of the Stenos, 99.2% of the Pseudomonas, only 90% of the Acinetobacter, and 97% of the Enterobacter ACA. However, the cautionary tale, this is the honeymoon phase. It literally just hit the streets in November. I don't believe it's been used, I could be wrong, yet at VCU. I talked to one of our PharmDs a couple of weeks ago. So very new. It's only approved for UTI right now. So there are some things we don't know. It looks incredible, but is it credible? Referring to the Credible CR study, a randomized open label study comparing cefiderocol versus best available therapy in carbapenem resistant gram-negative rod infections, including pneumonias, bacteremias, UTIs, et cetera. 101 patients got cefiderocol, 49 got BAT. In terms of cure, clinical cure, test to cure, cefiderocol performed pretty well. Appeared to do really about the same, maybe a little bit better than best available therapy. Here's the slightly confusing thing that is still very unclear. All-cause mortality was higher in the cefiderocol group at day 14 and day 28. And this has been reported by several news sources as basically coming from the company itself during a briefing, and is not published. And I looked again a couple weeks ago, it still wasn't published. So it's hard to know what to make of this. I am not overly concerned, but I will say that this is not a drug that at this time we have published experience with taking on a multi-drug resistant gram-negative rod ventilator-associated pneumonia, which in this document, that's where the problem was. It was the pneumonia patients with the non-lactose fermenting gram-negative rods. So there's this study, there's another one called Apex NP, which has sort of preliminary but not the final, comparing cefiderocol versus meropenem in these tough pneumonias. Hopefully we'll see publication and clarification in the next several months on this. I think it's important because cefiderocol appears to have remarkable capabilities. So to summarize the beta-lactam portion of this talk, The bacterial system chooses the defense system. We choose the weapon system. Now, here's the F-35 releasing I think a GBU pavemaker laser-guided bomb. I can't tell you if it's the 500 or 1,000-pound variety, but this pilot can choose a weapon that locks on by both laser and GPS. This is the bomb. It can steer itself with these fins and change its direction by 25 miles. It can be selected in multiple sizes of explosion. And this F-35 can be more lethal than 100 bombs out of a B-52, which is good because it has to carry the weapons internally and it has to open these doors down here, which makes it visible on radar. So if you're on a stealth mission, you just lit yourself up when you deliver the payload. Time to go home fast. Okay, in summary, for KPC, Class A, Vaporbactam or Relbactam may be more active, but Avibactam active. For Class B, Metallo, Aztreonam, you're going to get nothing from ceftolozane or Ava, Rel, Vaporbactam. Class C, AMP-C. It will be defeated by Ava, Vapor, Relbactam. It will be, actually, these guys are pretty stable, ceftolozane and cefepime, unless you get the AMP-C levels up real high. Oxa, Avibactam, but not Relbactam or Vabo. Porin mutation, ceftolozane. Efflux, ceftolozane. Cefiderocol against all. Moving to our next non-alcoholic friend, Acinetobacter. You see that intrinsic resistance, not too bad, but when it starts acquiring resistance, it goes bad real fast. We've talked about Pseudomonas acquiring multi-drug resistance. Well, Acinetobacter is just as bad, or perhaps worse. It really likes several of these things, more likely to pull in these metallo-B-lactamases, for example. Oxas, tougher. Again, with the porin mutes, the efflux pumps. It can deploy a combination of these things. Now, cefiderocol, again, would seem able to defeat all of these. We saw from the other study that it was active against almost all Acinetobacter, but we don't want to use cefiderocol unless we absolutely need to. Colistin, mutations in the PMR A and B protein, which can be sent out via sequence to look for. Quinolones, not too easy to defeat. And then aminoglycosides, defeated typically by aminoglycoside modifying enzymes. We have something new there. The new aminoglycoside plazomicin. Currently only approved to treat complicated UTIs. Just a reminder, phosphomycin will work against none of the germs that we've talked about in this thing, so don't go there. The claim to fame on this drug, it doesn't work any better than Gen-Ortobra against a Gen-Ortobra or amikacin susceptible organism. Doesn't work any better. It doesn't get any better tissue distribution than the basically poor distribution of aminoglycosides. Not thrilled with these drugs in a parenchymal pneumonia or an abscess or anything like that, but it is stable against many of the aminoglycoside modifying enzymes. So if you see an Acinetobacter or Pseudomonas that is resistant to all the aminoglycoside except plazomicin, it is because of aminoglycoside modifying enzymes that this drug is not being affected by. So another possible choice against Acinetobacter, it will not be useful against Burkholderia or Stenotrophomonas, which are intrinsically resistant to aminoglycosides. Colistin, old drug, new purpose, yes. A couple of quick points. Number one, colistin resistance uncommon in the US, much more prevalent in other parts of the world, like 27% in South Korea. This is critical because this has been the go-to drug for some of the worst of the gram-negative rods. And mutations occur pretty easily. That's what we would describe as a low genetic barrier. Resistance can occur a couple of different ways. One is mutations of the PMR gene, which can be measured quickly, or mutations that inactivate lipid A biosynthesis. Either way, you end up with a pathway that results in reduced functional LPS. I have an error in this next line below. There was a study that 266 patients with carbapenamase resistant Acinetobacter treated with colistin found that the colistin resistant had a lower mortality than the colistin sensitive. It's backwards here. Colistin resistance had a lower mortality when treated with colistin than colistin sensitive. Couple of things. A, it raises a whole lot of questions about colistin activity in general, as if I didn't have enough. And B, it raises this interesting question, was this serving as something that reduced the function of the bacteria, sufficiently crippling the bacteria? The bacteria, maybe it was already crippled or the mutations crippled it, but the functional changes may have improved mortality. Hard to say. Few words about Stenotrophomonas. We've covered that ceftolozane tazo, often a little bit more active than ceftaz. We've covered that ceftriaxone should usually be active. This was a useful study that looked at 41 isolates over a decade up to 2018 against many of the modern antibiotics. And the results were, susceptibility-wise, Levaquin did fairly poor, 29% sensitive. Bactrim, fairly poor, 37% sensitive. Minocycline was 93% sensitive and actually had the lowest MIC value of any of the agents tested, including tigecycline and including some of the newer tetracyclines, which I'm not really discussing today, ericycline and omadacycline. So it's really the best of the tetracyclines. Interestingly, tetracycline does nothing, but minocycline is pretty good on paper. And finally, Mr. Burke Holderia, good old Burke. Now, he is a lot like Steny, and the comments are quite similar, except, let's see here, colistin is not even on the option list, intrinsic resistant to colistin. So Burke Holderia, we might be looking at our minocycline, our ceftolozane, and our ceftriaxone. We're out of luck with the aminoglycosides. We're out of luck with the colistin. You might get a quinolone in there, maybe. You might get a Bactrim, but don't count on it in our patients. All right, so I'm going to wrap this up by saying there are many important topics that we cannot discuss today. At the top of the list, to keep that number of cefepime resistant or meropenem resistant, carbapenem resistant organisms as low as possible, and generally resistance as low as possible, active hospital epidemiology and antimicrobial stewardship programs are critical. We didn't talk about tissue and organ penetration, important. Biofilm, important. Combination therapy, interesting, lots to say, too little time, more that we don't know than we do know. And a final point here, which I think is very important, optimizing the dosing. So I think lots of times our antimicrobials get underdosed in these tough situations when we need deep tissue penetration in a badly infected lung. And here's a good time to call on our PharmD associates, continuous infusion, higher than standard dosing, balancing safety and efficacy, I think we can get more bang from the buck if we start employing these people in these tough cases. So, infectious disease 2020, emerging infectious diseases, global spread, emerging and expanding resistance, increased immune suppressed targets. That's right, everybody is on a biological response mire for their rheumatoid arthritis, their psoriasis, their colitis, transplant this, stem cell that, implanted devices, et cetera, et cetera. There is more infection potential and more global spread than any time in the planet's history. Versus our defenses, which are an evolving epi and stewardship programs, emerging molecular diagnostic capability, both of which we have in spades here, and then these new designer targeted antimicrobials, more killing, less innocent bystanders, safer, hit hard. It's an ongoing war that we must win. Google is a marvelous thing. I was talking about my service in the Navy. I was at my last service point, or my last station was the USS Independence. This is off the coast of Lebanon, 1982. I was there. Actually, I would have been right there. We left in December of 1982. Does anybody know what happened in April of 83? Our mission was a peacekeeping mission, shuttling the UN ambassador, Philip Habib, back and forth into the Beirut embassy, trying to negotiate a ceasefire because the Israelis were basically flattening the once beautiful Beirut. We left in 82, but we left some Marines behind, and in April 1983, there was an embassy bombing that killed several of the Marines I knew, several of the diplomatic personnel. So we'll just wrap it up with that. Any questions? Thank you very much.